This is exercise 4.8, question 17, proofs involving Pythagoras' theorem. Now we're given triangle ABC, where AC is perpendicular to BC, therefore we've got a right angle there at C. P is any point on AC, and Q is any point on BC. In part A of this question, we have to prove that AQ plus BP squared equals AB squared plus PQ squared. Now, straight away when we look at this question, we can see that it says PQ squared and there is no line PQ marked on the diagram. So the first thing we'll do is bring in the line PQ, which I've just done there. Then we can look at the question again and we can see that we need an expression for AQ squared. We'll need an expression for BP squared, an expression for AB squared, and an expression for PQ squared. So we're going to come up with those expressions now. In this first line of working here, we can state which triangle we're working in. So we've got in triangle ACQ, we can see that AC squared plus CQ squared equals AQ squared. So that's that first line of working there. Then we can see in the second triangle, BCP. Now we're doing this triangle because we want to come up with an expression for BP squared. So we look at BP, and BP is in the triangle BCP. So we come up with an expression for BP squared there. And we can see that PC squared plus BC squared equals BP squared. So we've taken care of these two things on the left-hand side of this equation. Then we can look on the other side of the equation. We need an expression for AB squared. Now AB is in the triangle ABC, and we can see that it's the hypotenuse. So therefore AC squared plus BC squared equals AB squared, which we've got written there in that third line. As I said before, we've constructed the line PQ, and so we need an expression here for PQ squared. We can see it's the hypotenuse of triangle PCQ. So then we say in triangle PCQ, PC squared plus CQ squared equals PQ squared. Now we can use those four statements and come up with an expression for AQ squared plus BP squared. Now, we start off here and we say therefore AQ squared plus BP squared is, we can see that AQ squared is AC squared plus CQ squared, so we write that in. We know that BP squared is PC squared plus BC squared, so we write that in. We can stop there. We can look at the other side of the equation, which is AB squared plus PQ squared. We can write those out and substitute the expressions that we've got for those as well. So AB squared is from here, AC squared plus BC squared. Just fix up that little squared there. And we can also see here that PQ squared, we make our substitution for that there, that it's PC squared plus CQ squared. Now we can see that both of those lines, both of those expressions are the same. They may not be in the same order, but they are in fact identical expressions. Therefore we can say that, because we can see AC squareds, we can see CQ squareds, PC squareds and the BC squareds are both there. Therefore we can say that those two expressions that I'm circling there are the same. Therefore AQ squared plus BP squared is equal to AB squared plus PQ squared. Reason, in brackets, that they are both equal to AC squared plus CQ squared plus PC squared plus BC squared. And that's part A of the question. Now in part B of this question, we are told that P and Q are the midpoints of AC and BC respectively. In other words, P is the midpoint of AC and Q is the midpoint of BC. Now, it doesn't look like that on the diagram. Diagrams are not drawn to scale most of the time. So even though it doesn't look like Q is the midpoint of BC, we have to take it that it is the midpoint. They've told us to let AC equal to 2x. So if AC equals 2x, I mean immediately we know that because P is the midpoint, that AP will equal PC, which equals x, because P is the midpoint of AC. So we can just write that's written up there, as you can see, and I'll just mark the diagram here with the x's, so AP equals x and PC equals x. Also in the hint that we've been given, we've been told to let BC equal 2y. Therefore, again, because Q is the midpoint, we would know that CQ is y. I'll just move that in. And we would also therefore know that BQ is also y. Reason being, so we can see that here, let BC equal 2y. Therefore, CQ equals BQ, which equals y, because Q is the midpoint of BC. Now, in this question, we have to prove that AQ squared plus BP squared equals 5 lots of PQ squared. Once again, we can see that PQ, that the line is not there. I'll just put that back in. Now, we can look at this first bit of the proof here. We need an expression for AQ squared. We can see that AQ is the hypotenuse of triangle ACQ. So we can say, well, AQ squared equals AC squared plus CQ squared. Now we know that AC equals 2x because we were told to let AC equal 2x, and CQ is equal to, as we've just set up here, CQ equals y. So we can expand that. So 2x all squared is 4x squared, y squared is y squared. Again, here we can come up with an expression for BP squared. Doesn't matter if you write it as BP or PB. So PB squared is part of the triangle PBC, and we can see it's the hypotenuse of that triangle, so we come up with an expression for that triangle. PB squared is PC squared plus BC squared, and again substituting in those values, we know that PC equals x from up here, and BC equals 2y, which is given in the question, so x squared plus 2y all squared. Expanding that, we get x squared plus 4y squared. Now in the question, we're asked to show that AQ squared plus BP squared equals 5 lots of PQ squared, so it'd be a good idea to add up these two expressions for AQ squared and PB squared. So we can do that now. So if we look down at the bottom of the page here, we can see that AQ squared plus BP squared is 4x squared plus y squared, which is up there, plus x squared plus 4y squared. And if we combine like terms, we can see that we've got 5x squared plus 5y squared. Now, we know that we can see that 5 is a common factor there, which is 5 lots of, we pull out the 5 common factor, x squared plus y squared in the brackets. Now, actually what I should have done first is just write up this expression here for PQ squared. Once again, we know that PQ squared is PC squared plus CQ squared. We can just put those values in, which is x squared plus y squared. So coming back down here, we know that x squared plus y squared happens to be PQ squared, so we replace this x squared plus y squared with PQ squared. Therefore, we can see that we've proven what we set out to prove, which is that AQ squared plus BP squared is 5 lots of PQ squared. And that's the end of the proof.